two-sample proportion test example. So here we have a study was conducted to compare the incidence of parasites in species of Mediterranean and Atlantic fish. In the Mediterranean Sea, 588 brill were captured and dissected. 211 were found to be infected by the parasites. In the Atlantic Ocean, 123 brill were captured and dissected, and 26 were found to be infected. So we want to test at the 10% level of significance whether the proportions of infected brill are the same at the two capture sites. And then we want to obtain a 90% confidence interval to estimate the difference between the proportions of infected brill at two captured sites. So what we're looking at here with the test for two proportions, they essentially give us two proportions here, the one from the Mediterranean, the one from the Atlantic. We want to use for the test statistic this P1 hat minus P2 hat all over the square root of P times 1 minus P, and then times the quantity 1 over N1 plus 1 over N2. So what are all these variables? Well, P1 is the proportion at the first population, and the proportion at the first population would just be the Mediterranean. And you could do this in another order, but I'm just going to go ahead and call the first one the Mediterranean. And we would have 211 over 588. So proportion of infected. For P2, it's just going to be 26 over 123. Now the P is what they call this pooled variance. And the formula for that is just x1 plus x2 over n1 plus n2. And in order to get the x1 and x2, we're just using the successful ones that were found infected. So we'd have the 211 for x1, and then for x2, we would just have the 26, and then we'd have this over the 588 plus 123, the two n's, totals that were selected. And when you put this together, you get 37 over 711. And then that means that 1 minus P is going to be 474 over 711 after you subtract. So we have all the information we need for the test statistic, and we can set up our null and alternative hypothesis here to get an idea of what we need to do for the Z. What are we looking for with the Z? And since we want to see if the proportions are the same, we are really just testing if P1 equals P2. And then the alternative would be that P1 is not equal to P2. And these would be the actual proportions that we're testing, and we're using the sample in order to do that. So whenever you're testing the not equal to alternative, what you really get then, or what you're looking for, is that Z is going to be greater than or equal to this Z of alpha over 2. And you could look at it as Z is less than or equal to the negative Z, but I always just use the positive Z here. And the reason I'm going to use positive Z in this case is because I know that P1 will be bigger than P2, so I'm going to get a positive Z in my test statistic in this case, just looking at the proportions up here. So if you got a negative value for Z, you would test it against the negative Z of alpha over 2 and see if it's less than that. But in a picture then, what we're looking at with this normal curve, for the 10% level, and since we're looking at not equal, this is actually a two-tailed test as they call it, so we're actually looking over here, and we split that 10% to be 5% on either side. And the cutoff in the standard normal, more importantly, table for this 5%, on the positive side, you have 1.645 for the Z value. So this would be our positive Z of alpha over 2, where our alpha here was 10%, level of significance. And then over here, we'd have our negative z alpha over 2. And that's going to be equal to negative 1.645. Now again, I'm pretty certain we're not going to need this based on how I'm subtracting P1 minus P2. But if you didn't see that beforehand, it is good to get both these values down. And you either got to be above this to reject the null or below this to reject the null. Okay, so let's go ahead and put these values into the z and actually see what we get here and decide if we're going to reject or fail to reject. So z would equal, and let's see here, we got the P1 hat, so 211 over 588, minus the 26 over 123, just grabbing all those values from up top, and then a big square root here, and then we would have the 237 over 711 times the 1 minus p, the pooled q, so to speak, and then we will have this 1 over the, let's see, n1 was 588, and then plus the 1 over the 123. So this is just the formula that you use to get the z. The development of the formula, they aren't going to go over it in an early stat class, and in fact, it takes a while. You really look at the theory if you're going to see the proof of why they use this. But overall, once you work this all out, especially at the lower level stat, that's the important thing. Just get a value from this, and we get 3.15. Well, that's way bigger than 1.645. That's telling us there's very little chance that the difference in our proportions is going to be close enough to say that the proportions are equal. We are definitely rejecting the null here. We're saying there's very little chance that these two proportions are the same. Statistically, based on our evidence, very little chance. When you're looking at the 3.15 and you're way, way, way out here, 3.15 is way out here, then that means that you have very little, extremely little chance of these two proportions being the same. So we would say here that we reject the null. And there is statistical evidence that the proportions are not the same. Okay, so that's testing at that 10% level. To do a 90% confidence interval, we're going to use a lot of the same information, just in a slightly different way. So 90% CI is all abbreviated here. The formula for the confidence interval in general is going to be the P1 hat minus the P2 hat. And then we're going to do this plus or minus the z alpha over 2, and then times the square root of this P1 hat 1 minus P1 hat over N1, and then plus the P2 hat times 1 minus P2 hat all over N2. And in this case, z of alpha over 2, with your 9% confidence interval, we are still looking at the two tails, so to speak, in our confidence intervals. So we're going to split this up into really 10% would become the 5, because alpha is 100 minus 90%, or 100% minus 90%. 10%, divide that by 2, you get your 5% again. So the z of alpha over 2 is still going to be 1.645 here. And if we start plugging in our numbers into this, our P1 again was 211 over 588 minus the 26 over 123. I'm going to go ahead and put this in parentheses because you can kind of do those separately, and then you do the plus or minus the 1.645 times the square root of the, let's see here, 211 times, that'll be 211 over 588 again, is the whole proportion. And then times the, let's see, that'll be 377 over 588. When we do 1 minus that, and need a bigger square root thing, so we'll do this all over 588. And then plus the 26 over 123, 97 over 123 when you do 1 minus that, and then all over 123. So really in these, I'm just trusting the formula here. The most work that has to be done is to get the z of alpha over 2. And again, always take whatever the difference is between 100 and the CI level and divide that by 2, and then use your z table in order to find the z value that goes with that. So when you work this out, the positive value, because we do have a plus or minus here, so the positive value ends up being 0.2162, and I am rounding. The negative value, when you subtract, ends up being 0.0787, and again, I am rounding. So that means our confidence interval, and more importantly, the 90% confidence interval, is going to be just 0.0787 up to 0.2162. And looking at this, what this tells me is that if I were to do many samples in the same way from the Mediterranean and Atlantic, looking at the parasites in Brill and make proportions, I would expect that if I'm doing a 90% confidence interval, 90 of them would capture, if I'm doing, let's say 90 out of 100, would capture the true value. So I don't know if this is one of the good ones, one of the 90% good ones, if I've done this many times in theory, or if it's one of the bad ones. But 90% is a pretty strong chance of getting a good one. So we're hoping that this is one of the good ones. And if it is one of the good ones, it indicates that the actual proportion of difference, or the difference in proportions, I should say, would be somewhere between 0.0787, or roughly 7%, 8%, to 20%. So overall, when I look at this, it's also another indicator that there is a difference between the two Mediterranean and Atlantic parasite and Brill proportions. If there wasn't going to be a difference between it, what I would be seeing then would be maybe a 0 captured in between. But I don't have that. I don't capture 0 in between. There's no 0 between 0.0787 and 0.2162. So that's one of the interpretations of the confidence interval. When you're using this to determine if there's a difference in two proportions, if there's no difference, you want your confidence interval to go from like negative to a positive so that 0 is in between. We don't have that. So another indicator above and beyond that test statistic approach that we used up above, that there is a difference between Mediterranean and Atlantic parasites in Brill in their proportions. Okay, I hope that helps with this concept, and thank you for watching.